Yes, welcome all for today classes for our heat transfer subject. And in the previous classes, we discussed about the basic terms which are used in heat transfer subject, and also mode of heat transfer. That is three mode of heat transfer. That is convection, conduction, and radiation. In the previous class, we discussed about the first mode of heat transfer. That is the conduction. Okay, in today's classes, we are go through the next mode of heat transfer. That is convections. Okay. Here it is the mode of heat transfer where energy transfer between a solid surface and the adjacent liquid or a gas that is in motion, and it involves the combined effect of the conduction and fluid motions. Okay, so conduction mode of heat transfer takes place between the two solid bodies or two solid substances or two solid equipments or two solid the components. Whatever the conduction mode of heat transfer takes place between the two solid bodies, those are come in contact with each other, then the and those two solid bodies are having the temperature different temperature. In that cases, what happens, the conduction mode of heat transfer takes place. But in this convection mode of heat transfer is takes place between the one solid bodies and the to the liquid or the gaseous. Okay, see here the the mode of energy transfer between a solid surface and the adjacent liquid, between the solid surfaces and the adjacent liquid or gas. So you can say that it is between the solid and liquid or gas, solid to the liquid or to the gas. But in the conduction mode of heat transfer, it takes place between only the solid surface, only between the solid and solid, or one part of the solid to the another part of the solid. Okay, so here the convection, it is a mode of energy transfer between the solid surfaces and the adjacent layer or gas that is in motion. That gas or liquid is in motion, and it involves the combined effect of the conduction as well as the fluid motions. Okay, so see here, this, if you are observing this figure, here it is one hot block is there. So this is the hot block, or you can say that a solid body. Okay, so over this solid body air is flowing, over this solid body air is flowing. Okay, so here the heat is transfers between the solid body to the air, to the air, through which mode of heat transfer? By convection mode of heat transfer. Okay, so there is one solid body, hot solid body. Over that solid body air is flowing. So now due to the temperature differences between this air and this hot body, what happens, our heat is transferred, from this hot solid body to the air, or you can say that gas, air. Okay, so this will shows the velocity variation and this temperature variation graphs. Okay, velocity, so as you move upward directions, the profile of velocity is more. Okay, so here the temperature exchange of heat, so near to this solid body is more, the temperature differences are, the heat transfer is more. So as it goes on in upward direction, the temperature or the heat exchange between the solid body to the hot air is less. These two are showing the velocity profile and the temperature profile of the convection mode of heat transfer. Okay, so this figure representing the heat transfer from a hot surface to a air by convection, air by convection mode. Okay, so uh, this much we should know. What is that? In the convection mode of heat transfer, the heat energy is transferred between the solid body to the air or to the liquid, to the air or to the liquid. Okay, another example, if you want to take it, if there is one hot water container, hot water container. Okay, so if you immerse one solid cold solid body into that hot water container, then what happens, the temperature, the heat is transferred from that hot water to the cold solid body. If you immerse that cold solid body inside the hot water, what happens, the temperature, heat of the hot water is transferred to that cold solid body. So that is also a convection mode of heat transfer. Convection mode of heat transfer. Okay, so this is the convection mode of heat transfer. Okay, next, the faster the fluid motion, the greater the convection heat transfer. Greater the convection heat transfer. If the faster the fluid motion, fluid may be an air or any gases or any liquid. If it is faster in rate, faster in motion, then greater the convection heat transfer. Greater the convection, remember this term, it is very important. If the faster the fluid motion, the greater the convection heat transfer. Okay, in the absence of any bulk fluid motion, heat transfer between a solid surface and the adjacent fluid is by the pure conduction. Pure conduction, that is, in the absence of any bulk fluid motion, heat transfer between the solid surfaces and adjacent fluid is by pure conduction. Okay, if the absence of any bulk fluid motion, if there is no motion of the fluid, okay, so that's why in the definition only it states that it is a combined effect of the conduction and fluid motion. Conduction and fluid motion. Okay, so this much about the definition of convections. Now there are two types of convections. One is forced convection, another one is the natural convection. Forced convection and natural convections. Okay, see here, these two are the classification under the convections. Okay, if the fluid is forced to the flow over to flow over the surface by external means such as fan, pump or the wind. Okay, if the fluid may be a air or gases, air or gases, so that fluid is forced to flow over the surfaces by external means such as fan, pump and wind. Okay, force is nothing but if you want to flow the fluid over the solid surfaces, then we can use some external devices. What are those? We can use the fan. Okay, we can use the fan, or we can use the pump or the wind. So we can forcibly we can uh, flow the fluid over the solid surfaces. Forcibly means by using some external devices such as fan, pump or wind. So such type of convection is called as a forced convection. Forced convection. So you can observe here in this figure. Okay, there is one hot egg is there, or you can say you can take any solid body is there that is very hot. Okay, so here you can use from fan. So through this fan you can force the air to flow over this hot egg, to flow over this hot egg. So what happens there, we can use some external means, we can use some external devices to force the air to flow over this hot egg. So such type of convection is called as a forced convections. You can use the fan, or you can use the pump, or you can use the wind. So whatever to flow the air over the solid surfaces, we can use some external devices. So such type of convection is called as a forced convection. Forced convection. Forcibly we can flow the air over the hot body, over the hot body. Now next one is the natural convection. Natural convections. Okay, see here, what is the definition of the natural, or you can say that free convections. Natural or free convections. If the fluid motion is caused by the buoyancy forces. If the fluid motion is caused by the buoyancy forces that are induced by density differences due to the variation of temperature in the fluid. Okay, see here in the second figure there is a hot egg again. Okay, so the air is flowing over the hot egg without any external devices. So in this we are not using any external devices to flow the air over this hot egg hot egg. So how it flows this air? So here it is caused by the buoyancy forces. It is caused by the buoyancy forces. Okay, that are induced by this buoyancy forces, induced by density difference. Why it is density difference? Due to the variation of temperature in the fluid. So that variation of temperature in the fluid means the temperature of this air is different from the temperature of this air. Then what happens? The buoyancy forces act. Then what happens? The air is flowing towards the upward directions, due to the density differences of the air. So due to the density differences of the air is nothing but temperature differences in the fluid. So naturally the fluid air is flowing. Naturally air is flowing over this hot egg. That's why it is called as a natural or free convections. Natural or free convections. So in this figure we are using some fans. We are using some fans to flow the air over this hot egg. But here we are not using any external devices. The naturally air is flowing over this hot egg. So that's why it is called as a natural or free convection. Natural or free convections. Okay. So now heat transfer process that involves change of phase of fluid are also considered to be convections because the fluid motion induced during the process, such as rise of the vapor bubble during boiling and fall of the liquid droplet during the condensation. Okay, so suppose if you are taken an example that uh, in that example if the phase of the water that means liquid water is get converted into a gaseous state. That liquid water droplet would get condensed into gaseous state. Or in the condensation process what happens that uh, uh, steam is get condensed, or the gaseous state of the water is get converted into the water droplets. So there is a phase transformations. What is the change of phases? Liquid to solid, or solid to liquid, or liquid to gaseous, or gaseous to liquid. That we call it as a change of phase. So if there is a heat transfer takes place, so due to that heat transfer there is a change of phase. Change of phase is nothing but solid to liquid, or liquid to solid, or liquid to gaseous, or gaseous to liquid. Whatever the change of phase takes place, such type of heat transfer is also referred as a convection. In that also the convection mode of heat transfer takes place. Okay, best example for this is change of phase is your cooling tower. So here the steam exit from the turbine is get converted into water droplet. Okay, so there is a change of phase from steam to the water droplet, that is gaseous to the liquid. There is change of phase. So such type of heat transfer is takes place by the convection mode of heat transfer. Okay, so convection mode of heat transfer takes place between the solid surface to the gases or liquids, and there are two types of convections. One is forced convection and natural convection. Forced convection is nothing but we can use the fan pump to flow or the air over the hot surfaces. In the natural convection what happens, we are not using any external devices or any external equipments to flow the air over the hot body. It is flow over the hot body due to the buoyancy forces. This is induced by the different density difference due to the variation of temperature in the fluids. Okay, next one is, so can you can say that all three mode of heat transfer modes will have uh, governing laws. So in the yesterday class we discussed about the conduction, and also there is a one law which is related to the conduction is uh, heat conduction, Newton's law of heat conduction. Okay, so here for convection we are having Newton's law of cooling, Newton's law of cooling here. Okay, so Fourier law of heat conduction is for the conduction processes, Newton's law of cooling is for the convection processes. Okay, so here he has given one equations. So this Newton has given one equations, that is Q dot convection is equal to HAS into TS minus T infinity. So that is measured in terms of what? Watt. Q convection is equal to HAS into bracket TS minus T infinity. That is H is equal to convection heat transfer coefficient watt per meter square degree Celsius. This H is nothing but what? Convection heat transfer coefficient. So this AS is nothing but the surface area through which convection heat transfer takes place, the surface area through which convection heat transfer takes place. This is the AS. S is nothing but a surface area through which the heat transfer takes place, and the TS is nothing but the surface temperature. Surface temperature, that is indicated by the TS, and the T infinity is equal to the temperature of the fluid sufficiently far from the surfaces. Sufficiently far from the surfaces. So this will gives the Newton's law of cooling. It is for you. It is this governing laws is related to the convection mode of heat transfer. Okay, so now what it states, the convection heat transfer coefficient H is not a property of the fluid. It is one coefficient, but it is not a property of the fluid. It is experimentally determined parameter whose value depends. It is experimentally determined value. This is not the property of the fluid. Okay, in the previous conduction mode of heat transfer we are using the K is the thermal conductivity, but the thermal conductivity is the property of the fluid, but here the H is not the property of the fluid, so that K value is different for the different materials. Okay, so that Ka dt by dx, K is the thermal conductivity, coefficient of thermal conductivity. Here it is the convection heat transfer coefficient, but it is not the property of the fluid, but the thermal conductivity is the property of the fluid. Convection heat transfer coefficient H is not a property of the fluid. Okay, so this value is experimentally determined upon whose value depends. Okay, convection heat transfer coefficient H varies, so it varies depends upon these parameters, with the type of flow, whether it is a laminar flow or turbulent flow. So this H values depends upon the type of flow, laminar or turbulent, geometry of the body. Okay, mechanism of heat transfer, flow passage area, the physical parameter of the fluid, average temperature, position along the surface of the body. So this H values varies depends upon these parameters. But this H is not the property of the fluid. Okay, so this is the Newton's law of cooling. Next, when H varies with the position along the surface of the body, for convenience in engineering application, its average value is considered. Average value average value is considered. It if the H value is different for the different positions, then we can take the average value. Average value we can take to calculate the heat convection. Okay, free convection, the H value varies from 5 to 35 watt per meter square Kelvin. So for the pre-convection process, this H values varies from 5 to 35. So in between these two value only we can take if it is a free convection. Okay, forced convection, the H value varies from 50 to 300 watt per meter square Kelvin. If it is forced convection, the value of H is 50 to 300. Okay, so here it shows the natural convections. Okay, natural convections, hot body is there over this warm air, cold air is flowing over this, and it will get the warm air here, warm air. Okay, so these are the some typical value of convection heat transfer coefficient, that is H. Okay, for free convection 5 to 35 values, and for force convection 50 to 300 watt per meter square Kelvin. Okay, so next one is thermal radiations. Third mode of heat transfer is thermal radiations. Thermal radiation. Okay, so first we should know the radiation. Radiation means what? The energy emitted by the matter. The energy emitted by the matter in the form of electromagnetic waves or photons as a result of change in the electronic configuration of the atoms and molecules. Electronic configuration of atoms and molecules. Okay, the energy emitted by the matter in the form of what? Electromagnetic waves. So as a result of change in the electronic configuration of the atoms and molecules, this is what radiation. Okay, so unlike conduction and convection, the transfer of heat by radiation does not require any presence of intervening medium. Intervening medium. Okay, so in the radiation mode of heat transfer, it does not require any medium to transfer the heat from one surfaces to the another surfaces. Okay, it does not require any medium, unlike conduction and convection mode of. So in the conduction mode of heat transfer also it requires some medium. Convection mode of heat transfer also it requires some medium, but in thermal radiations it does not require any medium to transfer the heat from one body to the another body. Okay, so next, in fact, uh, in fact heat transfer by radiation is fastest. So as compared to the conduction and convection, the heat transfer by the radiation is faster and it suffers no attenuation in the vacuum. This is how the energy of the sun reaches the earth. So one best example for this radiation process, radiation mode of heat transfer is the energy transferred from sun to the earth. Sun to the it does not require any medium or any interaction medium. Okay, it does not require any intervening medium. Okay, so as we already know that the radiation from the sun reaches the earth, so this is the best example for this radiation mode of heat transfer. Even though sun and earth is not come in contact with each other physically, they are not contacted, but that also even that also the radiation from the sun is in the form of electromagnetic waves will reaches the earth, will reaches the earth. So this is what the radiation mode of heat transfer. Okay, in a heat transfer studies we are interested in thermal radiations, which the form of radiation emitted by the bodies because of their temperature. See here, it is one example. So if you fire here, the wood, so it will emitted some energy. It will emitted some energy, and we can feel some heat to this hand, to this hand. So this is the mode of heat transfer. That is radiation mode of heat transfer. Radiation mode of heat transfer. We are not in contact with each other. So even though we are not in contact with each other, but we can feel that heat. That heat is from this fire. Heat is from this fire. Okay, so this is the also example for this radiations. Okay, all bodies at temperature above the absolute zero emit thermal radiation. Okay, next, radiation is a volumetric phenomenon. All the solids, liquids, and the gases emit, absorb, and transmit the radiation in varying degrees. Okay, it is a one volumetric phenomenon. All the solids, liquids, gases will emit or absorb or transmit the radiation in various varying degrees. All these are sometimes emit, sometimes absorb the uh, lights or energy. Okay, however, radiation is usually considered to be surface phenomenon of solids. It is also considered to be surface phenomenon, and it is also volumetric phenomenon. Okay, so you have to remember these two terms. Next, for this radiations, we are also having another laws of governing, that is Stefan Boltzmann's law. For conduction, what Fourier law of heat conduction. For convection, Newton's law of cooling, and for the radiations we are using the Stefan Boltzmann's law. Stefan Boltzmann's law. What it states here? It states that total emissive power of block body. So the total power emissive power of the block body is directly proportional to the fourth power of its absolute temperature. Total emissive power of the block body is directly proportional to the fourth power of its absolute temperature. That is, this total emissive power is directly proportional to the fourth power T raised to 4 of its absolute temperature. The absolute. Okay, so and here we can remove that proportionality sign, sigma into As, where sigma is equal to 5.670 into 10 raised to minus 4 watt per meter square in Kelvin raised to 4. So this value is called as a Stefan Boltzmann constant. Stefan Boltzmann constant. We have to remember this value. It is very important to solve some numericals on the radiation problem. Okay, so that is sigma is equal to 5.670 into 10 raised to minus 4 watt per meter square Kelvin raised to 4. This is the Stefan Boltzmann constant. Okay, so first statement is the total emissive power of a block body is directly proportional to the T raised to 4 or fourth power of its absolute temperature. Okay, so what is the black body? So idealized surface that emits radiation at maximum rate. Okay, if you are taken one black body, it emits all the radiation which is falling on that block body, so that emission of radiation is at maximum rate. So this Q radiation is equal to sigma As into T raised to 4 watt per. Okay, emissivity, a measure of how close is the surface approximate a block body for which E is equal to 1 for the surface, 0 is less than, E is less than 1. So that emissivity, this value is lies between 0 and 1. So that Q radiation is equal to emissivity into sigma into As into T raised to 4. This is the equation for the radiation. Okay, block body radiation represents the maximum amount of radiation that can be emitted from a surface at a specified temperature. See here, the block body, if it is a block body, it will emit the maximum radiation. It will emit the maximum radiation. So that's why the emissivity of the block body is always equal to 1. Emissivity of the block body is always equal to 1. Okay, so this with this we are completed the three mode of heat transfer, and also their governing laws. Okay, for conduction we are having the Fourier law of conduction. Okay, next for convection we are having the Newton's law of cooling, and for the radiations we are having the Stefan Boltzmann law. Okay, thank you.